Thank you. This is on. Can you all hear me? All right, hold on. There we go. All right, so yeah, my talk is simplifying complex UIs with finite automata and state charts, although I would have really liked to see a talk called simplifying complex talk titles with less words, but that's okay. I know what you all might be thinking right now. This new React API, a little bit scary, but I have some helpful advice for you. There's actually a really good book in order to understand how to best work with it, and it's doing whatever Dan Abramov says to do. I read this book, so I'm totally fine with the API, but funny enough, the second half of his talk is sort of exactly what I'm talking about today, except in a more general sense. So I want to talk about it, though, not in the context of React or Vue or Angular or any of the last 3 frameworks that came out last week, but I want to talk about it in a frameworkless context. Because this is an idea that doesn't just apply to any framework or no framework in general, but really any programming language as well, and we could see how it could help us simplify our UIs. So I'm a pianist. I've been playing piano for about 20 years, and so this is the approach that I take to software development, just trying to approach it with how I learn music. And so I made the analogy that if software is music, then developers are composers, because we're taking that music and we're composing it in a way that is applicable to any language or any platform, and we do so in a variety of ways. However, music's interesting because with music you have music notation, which you just saw there. Let's go back and see it. So this stuff right here. Now, this music notation is hundreds and hundreds of years old. However, the exact same notation is used today to represent music from Baroque, classical, romantic, whatever the hell Bjork is. It represents all of that in a declarative, succinct way so that you could give a musician who understands how to read sheet music and they will be able to play it. And this works for all instruments and all musicians of all levels. So I was wondering, what is the music notation of user interfaces? What do all user interfaces have in common, and how could we represent that declaratively? So when we're working with software, we usually deal with APIs. Now, APIs, or at least good APIs, have 3 main qualities. First of all, they're well documented. You could read the documentation and understand exactly what's happening with the API. They're also very predictable. The API is going to work the exact same way every time. And they're also testable. You could test against an API. They either provide mocks for you or have a test database or something like that. So user interfaces, though. User interfaces are really, really complex. I mean, does anyone find developing user interfaces easy? All right, so those of you watching online, no one raised their hand, which is good because I would have called them out if they did. We have to deal with something called a human API. That's all of you, that's all of our clients, everyone we work with. Human API is undocumented, we're unpredictable, and we're untestable, and we're also extremely buggy. If you don't believe me, just turn on an American news network, and you'll see proof of that. So I work for Microsoft. By the way, I'm not relating Microsoft to any of this terrible API stuff, I promise. And at Microsoft, we have more than 50,000 software engineers throughout the world, and at least 7 designers, I'm sure. And we also serve 1.5 billion customers, and I think this is just for Windows, so it might even be more than that. And so when we're developing user interfaces for 1.5 billion people, we have to just imagine all the different ways a user could use the user interface. And this is different cultures, different languages. You wonder why diversity is so important in tech? It's because we have to reach these 1.5 billion people. So we don't develop software for just one person. However, when we're developing software with just the happy path in mind, then that's essentially what we're doing. we're assuming that there's this ideal user who's using our applications in the exact way that we want them to. But this never happens. So we're going to take a look at a code example here. And I don't want you to read too deeply into the code. I just want you to see if you sort of relate to this. In this example, we're going to be creating a sample app where we query the Flickr API, and then we show the results. So very similar to what Dan was doing with movies in his last talk. OK, so it's pretty simple, right? We do a fetch. Then when we get the data, we show it. Are there any bugs here? Are we done? Well, let's say the data takes a long time to load. OK, so now we have to set this loading flag. Loading is true. And then once we finish loading the data, then we have to set loading to false. Are we done? No. What if we have an error? Well, we have to hide the loading screen, show the error, right? But are we home free yet? No, because we also have to make sure that we clear the error once we try to search again. And so, as you can see, the complexity is getting bigger and bigger. So now my onSearch event handler is getting extremely huge. And I'm sure that many of you could relate to this code. And many of you say, yeah, some of my code looks like that. Sure. And so what if your boss or your PM comes to you and says, we actually want the user to be able to cancel the search because sometimes it takes too long. Sometimes they want to search for something else. So that logic gets even crazier. I don't know if you could read that. I'll zoom in for you. But there's a lot of complexity in just one event handler. And so, of course, you might know this as spaghetti code, where our code quickly gets unmanageable. And some of you might be senior engineers, and you might be thinking, I don't do spaghetti code. All of my code is modular and layered and separation of concerns and all of that. And it's true, you might not write spaghetti code, you might write lasagna code, which is just a spaghetti code in layers. So this is called the bottom-up approach. And the bottom-up approach is whenever you have an event, like on-click or on-change or something, you do all of the logic in that event. And that logic could refer to just so many different actions, and some of those actions might change the state. But you have to choose which actions are executed carefully. Otherwise, you might edit the state in a wrong way, and you have to just add if, else statements and switch statements everywhere, and it gets really bloated really quick. In fact, there's a lot of downsides to this. First of all, this bottom-up code is very difficult to test because all of the application logic lives in your mind. So when you're writing your tests, you have to just output it from the developer's mind onto the tests, and it makes it really hard to work with other developers. Also, the code is difficult to understand. The code that I just showed you for showing and hiding the gallery, if you were to try to parse that as a brand new developer working on the project, you would find it really difficult to do so. The code will contain bugs for sure because there's going to be edge cases that you might not have considered. It will also be difficult to enhance, just like we've seen with cancellation. And features, such as cancellation, make the code worse. They explode the potential possible states and actions that could happen in your application. So here's some intuition for moving forward. First of all, we have the realization that UI components are not independent. We have all these frameworks that they isolate components and they say these components fit in their nice little box and we could just stick them in the page anywhere and they're just going to work. However, to the user, there's no such thing as isolation. Everything they see on the screen is in the exact same context, and we have to coordinate from components to component. So another realization is that actions, which is what happens when you do an event, are based both on the event executed and the current state, so the context. And it's also that this event action paradigm is too simple to represent all the possible states our app can be in. So what's the solution? Finite state machines and state charts. Now, I know that a lot of you might have heard of these before or might have studied it in school. And the problem, though, is that even though you might know what these are, you probably haven't applied it to user interfaces and applied it to actual software. So looking up material for this too could be a little complicated. So I'm a visual person. I'm going to do this in a very visual way so that we could break it down. So finite state machines consist of 5 parts. First, you have an initial state, such as it being idle. And then you have your finite number of states, which represents the states that the app could be in. And when an app is in one state, it can't be in the other state at the same time. You have a finite number of events, such as fetching, resolving, or rejecting a promise. You have a mapping from state to state based on these events. So for example, when you're fetching a promise and it resolves, you go to the fulfilled state, and same with reject and the rejected state. And then you have a finite number of final states, which we're not going to talk about too much just because user interfaces can be, continuous. We could just keep using them, and it's not like it says, all right, you're done using it. Go uninstall Instagram or whatever, because you're not going to need it anymore. And by the way, if you go to promisejs.org/implementing, it's going to say promises are just a state machine. So that should give you a big clue of what we're working with here. So the original app that I showed you, the gallery app, can be modeled as this state machine right here. So we start in the idle state, and then we go to search. Then we're in the searching state. If we try to search again, it just loops back because it's like, hold on, we're already searching. And then 2 things can happen. We could either resolve or reject the search results. And from those 2 states, we could search again. And so this is clearly seen by the arrows going from success or failure back to searching again. And so the state machine that I envision looks sort of like this. It's a JSON object, and I like JSON better than just black box functions, just because you could enumerate all the possible states, all the possible actions, and be able to transition from one to the other with a nice, simple function right here. So for example, if we're in the searching state and I get a resolve, then I just look it up in this JSON object. Just searching on resolve, success. And so, JavaScript, they call this I don't know, in TypeScript it's sort of a record, and I guess it's the same in C#, where actually it's a dictionary. In PHP, they call for help. I don't know. All right, so here's an example of what I just showed you. So if I were to search for Iceland, or actually, let's search for goats first. But let's say I don't want to search for goats. I'll just cancel that. So let's search for Iceland instead. There we go. So now you see we're in this gallery state, and when we do the events of selecting a photo, we have a state transition that transitions from gallery to photo. And then we could exit that. We could search again, cancel, search. Let's cancel that. Iceland. And so you see it goes from state to state, and no matter how many times I try to break this app, it's not going to deviate from this state machine that I have here. And you see there's a few extra things, such as actions over here, where when I'm done searching, update the items. We're going to discuss that a little bit in further detail. And also, this is part of an article that I wrote, which gives an introduction to finite state machines. So I use Visual Studio Live Share, or I don't use it, I work on it. I also have to use it. It's called dog fooding. Anyway, and this is sort of what it looks like. And so I don't know if we have Sarah and Burke in here. So here's Burke right now. And basically this, you could think of it as Google Docs for collaborative coding. It's right now in private preview at Microsoft, and I have no control over what they're typing, by the way, and they're typing this in real time. And so with this live share, we could collaboratively code in the exact same document at the same time. And so these are a complex series of events that are happening at the same time. And so we have to manage all of these possible events and all of the possible states that this could be, and I have no idea. Oh, God. Good luck breaking the demo. Well, it probably will, but anyway. So I'm gonna move on from this demo before it gets too crazy. One of the big things I had to work on in LiveShare is this whole sign-in flow, because you would think that signing in is easy and signing in, signing out, all of that. But it's actually not. Once you start drawing it out, it becomes a lot more complex. So for example, there could be a sign-in failure, especially from Iceland. I'm so glad that worked in Iceland, by the way, because all of our servers are based in the United States. And so when you have a sign-in success, then you go to the signed-in state. And from there, you could go do two things. You could either share a session, or you could join a session. And so what I did was, a couple months back, I refactored this part of the app so that it uses an explicit state machine, just like this, because we were getting a lot of bugs. We were saying, what if we're in the middle of sharing and the user signs out? Or what if we join a session and then we decide to share a session at the same time? That shouldn't be allowed. And so we had all of these if, else if statements and switch statements everywhere, and I decided there has to be a better way. So I just did, the simple JSON object approach, and we got a bunch of benefits from that. First of all, this state machine that I set up, it was very easy to add telemetry to it. So I added telemetry, and then I get this very nice visual showing exactly the frequency of how users go from state to state. And so you could see, obviously, most of the users go through this initializing and then signing in state. And then you could either externally sign in or you could sign out. And then you could see that users tend to go to either joining or sharing, at about the same frequency. And so it clearly shows, too, how many users go to the error state and how many users go to the success state for each of these states as well. Now, these are very powerful insights, because while telemetry will only tell you an atomic bit of data, here's telemetry that tells you the entire user flow of what's happening. And so we could limit this to user and be able to see a nice path of what the user actually did in the app. So it's sort of like, like those funnel diagrams, except even crazier. We could also use state machines for integration testing. And so this gets a little bit into graph theory, so bear with me a little bit. Over here, we would be using a shortest path algorithm. You could choose, your favorite one. Dijkstra. Is he Icelandic? Like, that sounds like an Icelandic name. Bellman, Ford, A star searching. Any of these formulas for finding the shortest path. And so for those who don't know, the shortest path is just going from one state to the other with the minimal cost. And so you can imagine each of these arrows have a weight. And so you just want to minimize, how long it takes to get from one path to the other. Sort of like in Google Maps, finding the shortest DTA from one point to the other. So analytics would provide these weights. And this represents all the happy paths a user could take, which means that, if we want a user to, let's say, share a session and get to the shared state, we would imagine the user going from signed in to sharing to shared, just that simple. And so these could be automatically generated from, the JSON structure or a finite state machine graph just like this. But remember, we're not just dealing with the happy path. So we would do a depth-first search algorithm to find all the other paths a user could take. So I know, some of you might be thinking, like, oh, these algorithm things, I didn't think I would need them. You sort of do, they're really helpful. And so these represent all the possible user flows. So you could imagine that a user getting from state A to state C might not take the easiest route. They might not go A, B, C. They might take a longer route to get all the way to C. And it also reveals all the edge cases, because when you model every single possible state with every single possible action and you get all of these flows, you're going to basically have 100,000% test coverage for anything that could possibly happen in your app. And of course, these could all be automatically generated. I'd caution against this, though, because you would be generating integration tests that, I mean, it would generate a lot of integration tests, which isn't necessarily a bad thing, but when you're doing continuous integration, you don't want your tests to take like 4 hours long. So it also makes software bugs visually clear. By drawing them out, having them on a diagram, you could easily see when I do this event, I'm going to the wrong state, or maybe I have an unhandled event, which does nothing, or maybe I have a missing transition. And so that's shown here too. For example, Dan was showing the example where when you click a movie, it just waits, and then you get the next movie, and there's no loading state. Well, you could clearly see that in the state transition diagram. And also, my favorite, race conditions. These are just made completely nil and void with state machines because you explicitly say, when I get this event, I go to this state. And if I get another event after that that I don't care about, it's not going to cause a race condition because I will just ignore that event. And that's what state machines can help with. Now, I want to talk about Herald state charts. And honestly, this could go on for hours and hours just because there's so much information here. So I'm just going to give you an overview of what these are and how these extend state machines in order to improve the way we look at user interfaces. Because user interfaces can get complex, and finite state machines might not solve everything. So with state charts, they're sort of similar to state machines. In fact, they're an extension of it, except we could have actions too. Actions are the things that actually do things to your state and to the app. We can also have guards, which prevent states from going from one to the other on a transition, if something doesn't match the condition. So for example, if I'm trying to search for something and the user didn't give me a search query, then I'm not going to transition to the next state. And so that could be declaratively modeled as well. There's also the idea of nested states and orthogonality. So this is parallel states. I don't want you to think of this as concurrent states where an app could be in two states at the same time, but I'll show you an example real quick. It's more a way of simplifying the number of states you have so that your state machine doesn't look all crazy. And also history, which is a very common feature that many users would want in order to go back to their saved state. So I created this library called XState, which models finite state machines and state charts in a declarative way, so that all you would have to do is use this JSON structure to model your state machine, and then you would get the next state by just calling transition on the current state and the action. It's functional, it's pure, so it's going to work in any framework or no framework at all. It also has the notion of actions, so it will return you an object telling you these are the next actions that you're going to take once you transition to a state. It also has guards, so you could pass in some external state, and it will validate against that external state and say, okay, well, this condition is met, so you go on to the next state. It also has hierarchy so that you could represent and compose state machines pretty easily. It has orthogonality so you could represent parallel states, and history so that you could also represent remembered states. In this example, let's say that you're doing a payment flow and you're either asking for cash or card. The user could switch between them. Then the user goes to the review page. You want to remember, did the user choose cash or card? So that's when you would just go to method.history and it would remember that. And this is a purely functional, no side effect type of thing. And so, you could imagine the applications of where you could apply this. One example of where you would use orthogonal states is this typical example of, let's say you have bold, italic, and underline. A user could click one of them, or two of them, or three of them, toggle all of them, toggle none of them, and it's represented by all of these 8 states. And you could imagine if we add more options such as align left, align center, justify, then it's going to explode into even more states. So with orthogonal state charts, we just have this very succinct representation of each of these possible states so that we know that we could go from bold on to off, italics on to off, and same with underline. and we could represent all of those at the same time. And also, hierarchy helps to reduce the number of arrows that you have in your finite state machine. So for example, both the success and failure states, we could search again and go back to the searching state. We could simplify this by just nesting them in a single state, the search state. And so this is fully supported by XState. And yeah, so you could imagine how this would simplify just really complex state machines. So I released XState about 6 months ago at React Rally. And since then, there has been a lot of development and a lot of people actually using it to make projects such as React Automata and others. And so pretty soon I'm going to be releasing another version, minor version, don't worry, nothing crazy, of XState, where we have improved the developer ergonomics, full I keep saying sexy XML, it's not sexy. Code is not sexy at all. SC XML support and conversion, a reactive interpreter, visualization tools, and a lot more examples. And so in order to actually show you what I'm talking about, here's an example of a visualization tool. So that same JSON object that you passed into XState, and the same one that I used for my gallery app, this is one of the one example of where you would use this. So let's see. So from here, my initial state is start, and I could just hover over this search action and go to this state, and then I could see the possible different actions, or sorry, events that I could take from this state. So let's say I have a search success, and so I go into the gallery view, and then I could either choose to search again, or I could select a photo, and so I could visually see what's happening in my state machine just by pasting in that JSON object. And so that's very hard to do with just a function. And that's why I decided to do it in a more declarative way. And so I'm going to be releasing this soon. I want you all to enjoy the rest of the conference before I release it so that you could have time to play with it afterwards. That's my excuse, at least. It's not out yet. Now, it would be, sort of remiss of me to not talk about sort of the downsides of state machines and state charts. But the truth is that you all are already creating finite state machines and state charts in your app already, and you don't even know it. However, the ones that you're creating are implicit, they're full of bugs, they're incomplete, and that's just the nature of how we code. So the advantage of finite state machines and modeling them in a very explicit way is that you reduce a lot of complexity up front just by getting rid of your if-else-if statements and getting rid of your switch statements and just having a direct mapping. However, that quickly explodes into many, many different states. So state charts help manage that with a little bit of higher complexity cost up front, but in the long run, you're going to see it's going to be very easy to add features, remove features, and handle different actions and different possible modes of your application. So, of course, there's a lot of advantages to using state charts, and the ones I'm going to quote here are not actually from me. They're from NASA. See, a few years ago, NASA had to send this little vehicle right here all the way to Mars. And they did so using state charts. And so the advantages that they said was, first of all, there's visualized modeling. So you could both model and examine the model of a state chart using visual tools. You get these precise diagrams that tell you exactly what's going to happen when certain conditions are met, when you're in a certain state, and this event happens. And when you're sending something to Mars, you can't exactly just send it there and hope that it works, right? You have to be absolutely sure that your billion-dollar project is going to handle every single possible state. And so they also use state charts for automatic code generation, which I mean, I'm not a fan of, but you could see how, it could be beneficial. Also, comprehensive test coverage. By using state charts, they were able to generate just all of these integration tests where they could test each and every one and ensure that every single state was being hit and every single possible action or event was being handled. Also, being on a big project, you have a lot of requirement changes. Like, we want to add this to the rover, we want to remove this functionality, we want to change the way this works. And when you're working on a big project and you have these late-breaking requirement changes, then things can get really stressful. With state charts, since you could clearly see the full flow of your application, you could easily add and remove features without worrying what's going to break, what's going to change, what's going to be affected. So there are some disadvantages as well. And the disadvantage is that my screen just went black. I guess that means there are no disadvantages. Anyway, since the rest of my slides are borked, I just want to show you this real quick. I gave a talk about 1.5 years ago. It was actually at JSConf Iceland, and it was about reactive animations. And funny enough, this is where I saw the primary use case for using state machines and state charts, because there was this really complex UI design that I really wanted to model, and I found it actually pretty difficult without using an explicit state machine or state chart. And so what I'm doing here is there's 3 different states, this one, and there's different actions as well. So the user could pan right, but just a little bit, and so I handle that as a transition from going from state A back to state A if, they didn't move far enough. But of course, if they move far enough, it goes to the next state successfully. And also it handles, like, if I'm going up and I decide to go left and right, it's not going to do anything because we're already going up and down. So it knows when this event happens, don't try to go to a different state because we're already transitioning to one state. And yeah. So I also want to mention 2 very good resources. The first one is on spectrum.io. It's spectrum.io/statecharts, and this is a community where we just talk about state charts, their possible applications, and how they're used everywhere. In fact, state charts are nothing new. They were invented by David Harrell in 1987, which is, 30 years ago? And so this is not cutting-edge stuff. And so if people are asking, like, why aren't we using state charts everywhere now? Well, the thing is, they are. In embedded systems or systems programming, people do use state charts in order to model their applications. We don't quite yet, but I think it's about time that we catch up to it. And so Eric Mogensen, who started this community, he made a wonderful resource called The Unfinished World of State Charts. And so over here, if you want to learn more information, there's a wealth of information here, including a ton of resources somewhere. But so that's at statecharts.github.io. And so I really want to encourage you to just revisit your application, revisit the way you think about things, and actually try to visualize things, because you're going to see that by visualizing your application, all of its possible states, all of the events that could happen, that you're going to have a clearer representation of the possible bugs, the possible features that you might add, the user improvements, and everything else. And so I want to thank you all for having me. Unfortunately, I can't show you my last slide because it's not working, but thank you.